Hello everyone and welcome back to this online NPTEL certification course on aquatic geochemistry. In our last lecture we were discussing the instrumentation required for chemical analysis, and I was talking about very basic instrumentation. I showed you just a few instruments that we use on a routine basis to do major cations analysis, anions analysis, elements, nutrients. More sophisticated instruments are required for doing different types of analysis. Sometimes we need to conjugate different instruments together to do a complete analysis. So, I just gave you just a glimpse of what we do on a routine basis, okay. But of course, depending upon the science that is needs to be done, you always have to go on modifying your methods and your instrumentation. Now, the basics of instrumentation is generating the data. So, you are collecting a sample for which you do not have any data, right, and we have to measure that, right. So, when we have to measure that, we have to have already know the values, know the estimates at least for some samples which the instrument will know, based on which it will tell me, okay, this is the value, okay. For instance, when we are measuring, how it is done. So, if I make a parallel comparison, okay, just for better understanding. So, the instrument is not going to measure direct concentration, okay. It is based on its own principle, it will measure some intensity, some counts, something like that, okay. Say for instance, if it is a mass spectrometer, its analysis will be in counts, okay. It will be counting the number of times the particles are striking its collector, okay. So, the number of ions that is being striking where the where the collector is. Similarly, if there is a spectrophotometer, there will be a absorbance unit, okay. So, at particular wavelength, what will be its absorbance, that is what you are going to get to know, okay. But from that absorbance value, how will you calculate either the concentration, or sometimes if it is reported in absorbance units, then that is okay, different. But to understand it in concentration terms, we need to convert those counts per second or absorbance units into our concentration. For that, we have to make what is called a calibration curve. Now, what is a calibration curve? As I have already discussed, when we were talking about sensors and all, that we prepare a certain known sample, okay, and then we measure that, okay, and we tell that instrument, okay, this is what X concentration looks like, this is what Y concentration looks like, okay. So, we give it like that multiple samples across our entire range. Say suppose my range is starting from 1 ppb to 1000 ppb, okay. So, across this 1 ppb to 1000 ppb, I will make multiple standards. I will probably make 8 or 10 standards and I will run it. So, 1 ppb, 10 ppb, 20, 50, 100, 200, 500, 750. So, like this I will make a range of standards, okay. So, what range you are going to do? Of course, that is depends on the sample concentration range, okay. So, based on that range, you are going to make a number of samples, you are going to measure those samples, and then you will tell that this particular sample has this much amount of say particular element, okay. So, the instrument will know, okay, this x ppm or x ppb, whatever it is having this much counts. Again another different y ppb, y ppm, whatever, that is giving you this much counts, okay. So, now like that we are going to make a curve. So, this is what is called a standard calibration curve making. So, here in this figure see, here is a plot, okay, for magnesium. Okay. So, this is showing in the x axis analyte, that is magnesium, which is measured in ppm, and in this axis it is measured in y axis, it is measured in counts per second. Okay. So, this is an analysis from the OES. Okay. Now, this is ICP OES. Okay. So, in this graph you see there is a value, there is my 0. So, that is almost like blank. So, yesterday I was talking about field blank, procedural blank, okay, reagent blank. So, that is a blank. Okay. So, that is blank, then that is my standard 1, okay. This is my standard 2. So, what is standard? Standards are things that we are preparing for known samples. So, I am preparing say something like magnesium standard. So, my magnesium standards will be, say suppose I am preparing for 1 ppm, I am preparing 10 ppm, I am preparing 50 ppm, okay, I am preparing 100 ppm. Okay, so, like that I will make at least 5 to 7 standards. Okay. Each calibration curve needs at least 5 to 7 standards. Okay. Now, this range, whether it is 10, whether it is this we can again depend on what is the range of your expected values. Depending on that you select a range and then you do the substandards. Okay. So, this is your standard 2, this is standard 3, this is standard 4, okay, and we are going to measure that, and we are going whatever the counts is going to come, okay, whatever counts is going to come, we are going to tell that okay, for this particular measurement this count is for my 10 ppm concentration, this one is for 50 ppm concentration. Okay. Now, when I have such a curve, okay, when I have created such a line, now when I am running, so this is again concentration and this is my counts. Okay. So, now when I am running an unknown sample, okay, a sample which for whose value I do not know, if I am trying to measure that sample, what will happen is I will get a particular count, right. So, I suppose my count is this, okay, then what I will do, I will just use the slope value and find out what is the concentration of that particular sample. But to do this I need to have this slope. So, this is very important, the slope of the calibration curve. Okay. The slope of the calibration curve, if this changes then my concentration value will change. Okay. And to do this calibration curve we need to have multiple standards, and maybe every standard we need to run in duplicate and triplicate. How are we going to prepare the standards? Okay. Now, these standards are prepared from as I said some known samples. So, either if say suppose if you are measuring a single element, then you will take a pure single element solution, you will take a magnesium solution, some salt of magnesium you will take and you will prepare a solution, okay, based on the concentration that you are looking. So, if you need 1 ppm magnesium, you calculate whatever salt you are using, that much amount ppm of magnesium should be there in that particular volume that is being measured. So, then you are going to prepare the other standards as well. Okay. So, what in multiple since in cations and in trace elements we are doing multiple elements, we generally have something called the multiple elemental standards. Okay. So, what happens is in the multiple elemental standards, you have a mixture of elements, okay, and these standards are extremely high concentrated. Okay. So, you will have maybe 10,000 ppm. So, you will buy something like this, a 10,000 ppm multi-elemental standard, and it can have all the elements, A to Z elements it will have, okay, depending, there are multiple types of there. So, in few elements, sometimes a particular standard will have few elements, some other standard will have lot many more. So, it depends on what type you are using, the multi-elemental standards will be there. So, from here we will go on diluting. By dilution we are going to prepare all the substandards, okay, and we have to be very careful when we are preparing our standards, okay, because slight differences in preparation of standards will change the slope of the calibration curve, and if my calibration curve is not good, then my data will not be good, okay, because as you can see my data depends actually on the slope, right. So, if my slope is not good, okay, if I do not have much confidence on the slope of the line, then my data will not be very accurate one. Very many times we have seen that the data is very sensitive to the slope, and we may have to run the same samples multiple times to get a very good accurate data, and that is because different people have different carefulness when preparing the sample. So, when you are preparing your sample, you have to be extremely careful when you are preparing these standards. Okay. Now, so this is the method for standard calibration. Now, there is another technique called standard addition. Now, standard addition is another very specific technique for analyzing elements that are extremely low in concentration or are very difficult to measure beyond below a certain value. Say for instance, you are trying to use an instrument whose detection limit for a particular element is, say suppose 1 ppb. Okay. So, the detection limit is 1 ppb. Now, you know that in your sample it may so happen that it is less than 1 ppb, because if you are analyzing it without any standard addition, it is just not measuring the it is showing below detection limit. So, what you can do is you can then try this standard addition technique. Okay. If you do not want to do a lot of other separation and enriching and all that, standard addition technique is there. In that what you do, you prepare an artificial standard of 1 ppb. Okay. 1 ppb standard is made, and then we are going to add that to your unknown sample. Okay. To my unknown sample, I am going to add by 1 ppb solution, and now I am going to measure it. So, what will happen, it will come in say suppose 1.00 say suppose x ppb. Okay. So, my final value, then I will subtract the 1 ppb. Okay. So, I will subtract the 1 ppb value because I have added it artificially from outside. So, then it will give me that actual value concentration, I will get that. Okay. Now, generally this is the standard addition technique is done to correct for matrix effect. Okay. That is a particular term called matrix. Okay. Now, what is matrix? Matrix is basically the nature of the kind of water itself. So, for instance, different water types are having different properties, okay, based on its chemical constituents. The properties will be slightly different, okay, and this is mostly the constituents I am talking about, organic constituents. Okay. So, organic rich, organic poor. So, the matrix is sometimes gives us different values for a same sample. If we measure in so what I am trying to understand, if you have a matrix effect, okay, matrix effect means the nature of the water itself. The nature of the water meaning, say suppose river water, okay. Now river water, if that water is low in organic concentration, then that water analyzing constituents in that water, all the elements will be much easier, okay. But if that water is rich in organics, then what will happen is organics will start interfering when you are analyzing the sample in the instrument, okay. So for that what will happen is we will get slight differences in the values, okay. Now when your range of detection has to be very sensitive, matrix can be a very big issue. If you are measuring an element whose variation you are seeing in the second decimal degree or in the third decimal degree, okay, at that time matrix related correction has to be very precise, otherwise you will not know whether that variation is due to matrix effect or actually the sample has that known. So this is what is called matrix. Now matrix, as I again said, depends on the water type. So if it is fresh water, if it is saline water. So what will happen in saline water? You see saline water, as I say, that is saline in nature, higher ionic strength, okay. There will be high concentration of sodium, of chloride. Now what will this sodium and chloride do? It will, since we are not in any doing any other kind of removal, so sometimes people try to remove the sodium and chloride and make it in a particular different same matrix, okay. So what they will do, they will evaporate the sample, okay, they will completely evaporate the sample. So they will take, suppose in a small beaker they will take 5 ml of the sample or 10 ml of the sample, then they will completely dissolve, they will completely evaporate the sample. Then they will artificially add maybe a very dilute acid. So 1% nitric acid, 1% double distilled, okay, 1% double distilled HNO3, okay. For ICPS analysis, this is what I am talking about. So this kind of acid will be, solution will be added, and then it will be go for a instrumentation analysis, okay. So what will happen is that all my samples will have this as the matrix. Then the instrument, there will be no difference, no effect, no matrix sample matrix related effect. But if I am not evaporating my sample, I am just measuring the sample as it is, just making it 1%, just adding a very dilute acid, okay, then I am running the sample. Then due to the organic concentration, there might be certain matrix effect. Now to correct for that matrix effect, we are going to sometimes add this called an artificial element as a standard addition, okay. Say suppose I am making, commonly the elements that are used are indium, yttrium, okay. These elements, okay, you will see that these elements, they are not very commonly found in nature, okay, indium, yttrium, they are not very commonly found in nature. So what will happen if I am artificially adding, say suppose I make a 5 ppb solution of indium and I am adding it to all my samples, okay. When I am adding it to all my samples and I am measuring it, sometimes I will see that my measured value is 5.001, or sometimes I will see I am measuring 5.98 ppb, okay. So I know that this difference from 5 ppb is what is due to the matrix, okay. Due to the matrix of the sample itself, the instrument, there was some instrumentation related challenges, due to which the value that I measure of indium is little more or little less. Now this correction will be applied to all other elements, Okay, such correction will be applied to all the other elements, and then finally after blank correction, after matrix correction, I am going to get my value. Okay. Now, how do I know that whether the value that I am measuring is correct or not, right? My calibration curve I am preparing in my lab, I am preparing these samples, okay, I am preparing these standards and I am measuring them, and I am also adding this matrix, that also I am preparing and I am going to measure that, right. Now, how do I validate my entire method? So, for that there is something called the standard reference materials. Okay. I am going to analyze certain standard reference materials or certified reference materials as an external sample. Okay. It will be run as an unknown sample. Okay. So, the commonly used ones for water analysis will be like this one, like the 1643F, okay, which is from this agency called NIST. Okay. It is a USA based agency and it prepares such kind of standard reference materials, and all over the world okay, people, scientists, they use these standards. Another is this one, this is the SLEW, which is a form of estuarine water. Now, what is the difference between the two? 1643F is a completely artificial standard. That means they have prepared it, okay, in their lab with known concentrations of particular elements. They have prepared the this particular standard. But for SLEW it is different. SLEW is a collected natural water. So, as it says, it is an estuarine water. Okay. So, this agency NRC, which is the National Research Council in Canada, they collected some estuarine water and they measured the constituents in that particular sample, and not only they measured in their lab, they also have sent this particular sample to to multiple labs all across the world, and then they finally get the give the common okay data. Okay, so they will see, okay, this element, it is being measured in different labs all over the world. So, what is the final mean value that they are getting, plus minus a standard deviation, that is the error that is will be there. So, that they will report, okay, that they will certify. Okay, so, this is SLEW and this is suppose it is calcium value is so and so milligram per liter and this much error is acceptable. Okay. How do they know? Because they have sent it to so many labs and all the labs have given their reports. They have done a quality check, then they will give the interlaboratory report. Based on that interlaboratory report, they will finalize their concentration. Okay. So, this SLEW happens in batches. Okay. SLEW preparation happens in batches. Why? Because every time a batch is collected, it gets sold out, then you need a fresh batch. So, again a new batch is collected. Similarly, new values are certified, then again it comes into the market. So, it comes in different numbers. So, there will be SLEW 1, SLEW 2, SLEW 3, SLEW 4 like that. Okay. So, like that it will come. Another extremely important factor that one has to keep in mind is accuracy and precision check. Okay. What is accuracy? Accuracy is the closeness of a particular measurement to the true value, right. So, I said that when we are measuring unknown samples, we have to measure a particular CRM, right. That is the standard material that we are going to say, okay, this standard reference material I measured, I got the actual value. So, suppose in the standard reference material, my calcium is 50 milligram per liter, say, okay, and I measured this standard and my calcium value was 49.5 milligram per liter. So, I know okay, this 49.5 value is very close to 50 milligram per liter. Okay. So, that is my accuracy, how accurately I can measure a particular element close to its true value. Okay. So, that is my accuracy. So, for accuracy check only, we always going to measure the external sample, that is a SRM. Okay. Now, what is precision? Precision is when we are making the measurements, but they are very close to each other. Say suppose I am repeating a sample 10 times, okay, and every time the values are coming 48.4, 48.3, 48.1, 48.0, okay, like this I am going to get 10 values. Okay. So, every time I am seeing it is closing in around 48, right, but my actual value is 50, right. So, it is off from 50, but it is closing very in around 48. So, this is my precision, okay, that every time when I measure I get this value something around 48, 48 point something, 48 point something, right. So, that is my precision, this is my accuracy. Okay. So, here if I see in this graph, if this is my, say suppose this is my true value, okay, the inner circle is my true value, okay, this one is my true value. Okay. So, inside my true value I have only, I take multiple measurements, okay, then I have one here, one there, all are there. So, this means it is not only not accurate, but it is also not measuring precisely. Okay. Then again I take the same thing, I take a same sample and I measure, and all the values fall here, okay, that is far from the true value, okay, which is far from the true value. Okay. So, that means it has a low accuracy because it is falling far from the true value, and it is also having high precision, okay, because these values are very close to each other, right. So, since they are very close to each other, it has a high precision. So, means every time you measure it, it will fall somewhere here, okay. And in this plot, it is showing that it is a high accuracy, but it has a low precision. That means sometimes it is saying right, sometimes it is falling outside the true value circle, right. Sometimes it is falling outside the true value circle, but sometimes it is falling inside the true value circle. So, that means the precision is low, but the accuracy is high, okay. But this is very dangerous to understand. This is also dangerous, this is also dangerous, this is also definitely dangerous, okay, because which one you are going to consider you do not really know, right. Only that means what you have to do is then that you will only consider this 2 or this 3 and you have to delete these 4 values, right. So, you will take 6 values, out of that 2-3 values you are going to keep, out of the and the rest of them you are just going to remove it, okay. The best case is when you have high accuracy and high precision. That means as many as number of times you are going to measure, you are going to get the same, the values will fall inside the true value circle and it will be very close to each other. So, this is the best scenario. Now, in all other scenario, this one specifically, this one where is high accuracy but low precision, this particular case you may have to improve your method, okay. Maybe some instrumentation method if you improve, then your values will again this for this, it will come inside this circle, okay. This shows that there is some either problem with your instrument or with the reagent. So, something it is doing that you are sure that the instrument is measuring it right, but due to the reagent or due to some handling error that it is falling outside your true value circle. Okay. And this particular scenario shows that you have to take care of a lot of things. So, you have to take care of your handling of the sample, you have to take care of the reagent preparation, you have to take care of your instrumentation, because you do not know what is causing the lack of accuracy also and the lack of precision also. Okay. So, from this first scenario we slowly move to the second scenario, then we move to the third scenario, and finally, this is our final results. Okay. Now, this sometimes we have to establish for a particular analysis type, we have to establish in our own instrument, in our own lab. Okay. Now, another thing that we need to know is the limit of detection, okay, LOD. Now, what is the limit of detection? This limit of detection is the lowest light that can be confidently distinguished from the background signal. Okay. So, of course, all instruments they will have some background value, okay, some noise kind of thing will be there. Okay. So, that is your background, and whatever you can confidently say that okay, the last value on which you will be very confident, the lowest value that on which you will be very confident, that stands as your limit of detection. Okay. Now, limit of detection for each element will be different, okay, and it depends on the instrumentation type, the principle, and the sensitivity of the technology and everything. So, that is your limit of detection, which mostly depends on the instrument that you are using. Now, limit of quantification, this is something that we are going to report in our data as the detection limit. Okay. So, this limit of quantification is the lowest concentration that can be measured with the acceptable precision and accuracy. Okay. So, in our lab we prepare samples, okay, we are going to measure the calibration curve. Okay. Now, based on our calibration capability, the lowest concentration that we can absolutely with full confidence that we can say that will be our limit of quantification. So, for me, if I am going to measure 0.001 ppb, okay. So, if I am going to measure 0.001 ppb, then I am going to say okay, this is my limit of quantification. Now, this again limit of quantification varies for every element. Okay. For certain elements it can be in the first decimal degree, for some it can be in the second decimal degree, for some it can be in the third decimal degree. Okay. Depending on the sensitivity of that particular element to the principle of the instrument that you are using, there should be no interfering ions and other things. So, based on that your values will come. Another important aspect when we are talking about limit of quantification is the blanks. Okay. Most of the times we have seen that by reducing our blank values, our limit of quantification can greatly be enhanced. Okay. That means my concentration we can go down much further. So, we have to use better quality of acids, that means from single distilled acids we can use double distilled acids, like you just use cleaner and cleaner substances. So, acids, water, then the vials that you are preparing, if you are touching, so the gloves that you are wearing, okay, the room that you are in, everything, okay, everything accounts when you are going to prepare the sample, when you are going to analyze the sample. Okay. Then comes our reporting of the data. How do we report the data, right? So, when you see this particular value, you see how in there are multiple digits in the decimal places, you can see. So, when you are going to analyze your sample, based on how you are measuring, the report can come in 5-6 digits, right. but you are not going to report in that way. We have to limit ourselves. So, if you are measuring, say suppose a value of 5.4, 6, 7, 8, 9. So, this is my something ppm. Am I going to report it like this when I get the value? Am I going to report it like this? How do I know where to round off? To which digit I should round it off? Okay. That depends on the instrument detection limit. Okay. If you are measuring your samples, okay, and you know that your detection limit is in the second decimal degree, there is no point in giving the extra 3 digits then. Okay. You have to round it off to the second decimal place and then report the data. If you give 10 values also after that, 10 numbers also after that, it is of no use, because I know that beyond this digit there is no confidence, right. Beyond this particular digit there is no confidence. So, we always, if you see, this is example of the certified values of this particular SRM 1643F. Okay. And you should note that some is reported in the first digits, some are reported in the 2 digits, okay. Certain are reported in 3 digits, okay. Certain are reported in 4 decimal degrees. So, 4 decimal digits, some will have no decimal digits at all, right. So, then you should understand that when we are reporting the data, we should report it in the similar manner, okay. That when I am writing calcium, I will know what is my limit of detection. If I know that my limit of detection is 0.01 milligram per liter, I will report it only up to the second decimal degree and not beyond that. Same thing, say suppose I am measuring lead and I know that my limit of detection is 0.001 microgram per liter, then my whenever I am reporting, that should only be limited to third decimal degree. Okay. So, with that I finish this lecture. In the next lecture we are going to see some water quality parameters, the most common water quality parameters. So, see you in next class. Thank you.